Welcome to True Projects. In this video, we are going to explain about the project title, an enhanced AI-based network intrusion detection system using generative adversarial networks. Introduction. The primary focus of the project is to improve the capabilities of network intrusion detection systems (NIDS) by leveraging generative adversarial networks (GANs). These GANs are used specifically to tackle the challenge of data imbalance within AI models, which often affects the accuracy of network threat detection. By generating synthetic data representing underrepresented attack patterns, the aim is to refine the system's ability to detect and respond to these threats more accurately. The context of this project arises from the growing concerns surrounding network security. With rapid technological advancements, there's an increased vulnerability to cyber threats, prompting a concentrated effort in researching AI-driven anomaly detection systems like NIDS. This context emphasizes the urgency and significance of the project's objectives within the broader landscape of network security. One of the key methodologies employed involves leveraging advanced generative models (GANs) to create synthetic data. This synthetic data specifically addresses the underrepresentation of minor attack patterns within the existing datasets. By incorporating this additional data, the project aims to enhance the overall performance and accuracy of the NIDS network intrusion detection system, ultimately improving its ability to detect a broader spectrum of threats. The project's efficacy is validated through comprehensive evaluations conducted on various datasets, including real-world enterprise data. These evaluations serve to confirm the superiority of the enhanced NIDS over previous iterations of AI-based NIDS. The results showcase a marked improvement in accuracy in identifying and mitigating network threats, affirming the effectiveness of the proposed enhancements and methodologies. Objective. The proposed system focuses on rectifying data imbalance within AI models used for intrusion detection. It achieves this by employing advanced generative models specifically designed to create synthetic data representing minor attacks pattern. By generating this synthetic data, the system aims to balance out the representation of various attack types within the datasets used for training. This approach helps to elevate the issue of skewed or inefficient data for less frequent attack instances, ultimately enhancing the model's ability to accurately identify and classify these threats. The project conducts a comprehensive evaluation of various models encompassing both deep learning architectures such as convolutional neural network (CNN), deep neural network (DNN), long short-term memory network (LSTM), and traditional machine learning algorithms like support vector machine decision tree. Additionally, torch-based implementations of these models are considered. Each model has unique strengths in capturing patterns, handling different data structures, and learning representations. By evaluating these diverse models, the project aims to identify the most effective approach or combination of approaches for robust intrusion detection. The project involves thorough evaluations and assessments using diverse datasets to quantitatively measure and demonstrate the enhancement achieved by the proposed system. By comparing the accuracy and efficacy metrics against prior AI-based intrusion detection system, the project aims to showcase the tangible improvements achieved in detecting and mitigating network threats. This demonstration not only validates the effectiveness of the proposed enhancements, but also provides concrete evidence of the system's superiority over previous iterations. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing necessary libraries or modules in the programming environment to access specific functions or tools required for data processing, visualization, machine learning, and deep learning tasks. Commonly used libraries include Pandas for data handling, Matplotlib and Seaborn for visualization, sklearn for machine learning tasks, and TensorFlow or Keras for deep learning. Exploring the dataset. IoT23 dataset, NSL KDD, and UNSW NB15. This phase involves exploring multiple datasets relevant to network intrusion detection. The IoT23, NSL KDD, and UNSW NB15 datasets are specifically used. Exploratory data analysis is performed to understand the structure, patterns, and characteristics of the data. It includes examining data distribution, statistical summaries, identifying missing values, and understanding the nature of features present in the dataset. Data processing involves preparing the data for analysis. This step includes transforming raw data into a suitable format for further processing. It involves converting data into a Pandas data frame or a Keras data frame, removing or handling unnecessary columns that do not contribute to the analysis, ensuring data cleanliness and consistency. Visualization using Seaborn and Matplotlib. Utilizing Seaborn and Matplotlib libraries to create visualizations such as histograms, scatter plots, bar plots, etc. to gain insights into the data. Visualizations help in understanding data distributions, relationships between variables, outliers, and trends. Label encoding using label encoder. Label encoding is a technique to convert categorical variables into numerical format, which is often required for machine learning algorithms. The label encoder tool is used to assign unique numerical labels to categorical data, making it easy for algorithms to process. Feature selection using select percentile using mutual info classify. Feature selection involves choosing the most relevant and informative features for the models. Select percentile with mutual info classify is a method that selects the top percentile of features based on their mutual information for the target variable. This helps in focusing on the most influential features, reducing dimensionality, and potentially improving model performance. Splitting the data to train and test for deep learning and X and Y for ML. The dataset is divided into training and testing subsets. This separation allows for model training on a portion of the data and subsequent evaluation of the trained model's performance on unseen data. For machine learning and deep learning tasks, typically X denotes the input features and Y represents the target variable. Building the model involves creating and training various models such as deep learning architectures, CNN, LSTM, and machine learning models, SVM decision tree, for network intrusion detection. This step includes configuring and training the models using the prepared datasets to learn patterns and make predictions regarding network intrusions. Training the model. This step involves feeding the prepared data into the chosen machine learning or deep learning models and training them on the labeled dataset. The models learn from the input data, adjusting their parameters to minimize errors or maximize accuracy depending on the type of the problem, classification or regression. Flask framework with SQLite for sign-up and sign-in. Integration of Flask, a Python web framework, along with SQLite, a lightweight relational database management system. This combination enables the creation of a user management system with functionalities for user registration sign-up and authentication sign-in within the project's interface. User gives input as feature values. Users interact with the system by providing input in the form of feature values relevant to the network intrusion detection task. These inputs include various metrics or characteristics related to network traffic or potential threats. The given input is pre-processed for prediction. Any input provided by the user needs to be processed and formatted appropriately before it can be used for prediction. Similar pre-processing steps as in the initial data processing phase may be applied to ensure that the input aligns with the model's requirements. Trained model is used for prediction. The pre-processed user input is fed into the previously trained models to make predictions. The trained models leverage the learned patterns from the training data to predict the likelihood of network intrusion based on the provided user input. Final outcome is displayed through front end. The final outcome, which could be the predicted classification or any relevant output of the intrusion detection models, is displayed to the user through a front-end interface. This user-facing interface provides some means for users to interact with the system, receive predictions, and view the results of the intrusion detection analysis. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is CNN, Convolutional Neural Network. CNN are deep learning models primarily used for image classification but also applicable to sequential data like network traffic analysis. They employ convolutional layers to automatically extract relevant features from input data. These layers capture patterns in the data, making CNN effective in identifying intricate structures. DNN, Deep Neural Network. DNN are a class of neural networks consisting of multiple hidden layers between the input and output layers. They excel in learning intricate patterns in data by processing information through these hidden layers, which enables them to handle complex relationships within the input data. LSTM, Long Short Term Memory. LSTM is a type of recurrent neural network RNN specifically designed to model sequences and time series data. It addresses the vanishing gradient problem in traditional RNN, allowing it to capture long-term dependencies in sequences, making it suitable for analyzing temporal data like network traffic patterns. CNNG, torch-based CNN, DNNG, torch-based DNN, LSTMG, torch-based LSTM. These models denote CNN, Convolutional Neural Network, DNN, Deep Neural Network, and LSTM, Long Short Term Memory architectures implemented using the Torch framework, which is a popular deep learning library in Python. Torch provides efficient tools for building and training neural networks and is known for its speed and flexibility in deep learning tasks. SVM, Support Vector Machine. SVM is a traditional machine learning algorithm used for both classification and regression tasks. It separates data points into different classes by finding the optimal hyperplane that maximizes the margin between different classes in the feature space. Decision tree. Decision trees are simple yet powerful algorithms that utilize a tree-like structure to make decisions based on feature values. They recursively split the data based on features to create a tree structure, making them interpretable and suitable for both classification and regression tasks. In the extension phase of the project, an ensemble model is introduced. Ensemble models combine the predictions of multiple base models to improve overall accuracy and robustness. Comparison graph of IoT23 dataset. In this project, we have utilized IoT23 dataset. IoT23 dataset comprises network traffic data collected from Internet of Things IoT devices across 23 different categories. It includes a variety of network activities such as normal user behavior and potential intrusions or attacks. Each category represents a specific type of IoT device and its associated network traffic patterns. This is the accuracy comparison graph of IoT23 dataset. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have the algorithm name. In this project, we have also utilized NSL KDD dataset. NSL KDD dataset is a refined version of the KDD Cup 1999 dataset. It's used extensively for evaluating intrusion detection systems. The original KDD Cup 1999 dataset had several limitations such as redundancy and irrelevant data. NSL KDD addresses these issues by eliminating duplicate records and maintaining a better balance between attack types. This is the accuracy comparison graph of NSL-KDD dataset. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. This is the F1 comparison graph. On the x-axis, we have the F1 score, and on the y-axis, we have the algorithm name. We have also utilized UNSW NB15 dataset in this project. This dataset is a network traffic dataset generated in a controlled environment to mimic a real-world network. It includes various types of attacks and normal activities. UNSW NB15 is known for its comprehensive nature, containing detailed features such as source and destination IP addresses, protocols, service information, and attack categories. This is the accuracy comparison graph of UNSW NB15 dataset. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. This is the F1 comparison graph. On the x-axis, we have the F1 score, and on the y-axis, we have the algorithm name. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contains algorithm information which will be loaded into the project code during runtime. These are notebook.ipynb files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, which is this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created. So I'm entering the username and the password and then click on sign in. So we have logged in successfully. So here we need to enter all these parameters to predict the intrusion detection. So I'm entering the parameters now. So So here I have entered all these parameters. So the first one, service is 19. Service is the types of network services or protocols used within the network traffic. Flag is 9. Flag indicates various packet attributes or states in network communication. SRC bytes is 491. Number of bytes sent by the source host in a network transaction. DST bytes is 0. Number of bytes sent to the destination host in a network transaction. Count is 2. Number of connections to the same host as per the dataset record. Error rate is 0. Percentage of connections that have SYN errors over a period. Same SRV rate is 1. Rate of connections to the same service as per the dataset record. Different SRV rate is 0. Rate of connections to different services as per the dataset record. DST host SRV count is 25. Number of connections to the same service on the destination host. DST host same SRV rate is 0.17. Is number of connections to the same service on the destination host. DST host different SRV rate is 0.03. Rate of connections to the same service on the destination host. DST host error rate is 0. Percentage of connections that have SYN errors to the destination host. After entering all these parameters, click on predict. So here we got the result. There is no attack detected and it is normal. So in this way, we will enter another set of parameters and check whether attack is detected or not. So here, I'll be entering another set of parameters now. So here, I have entered another set of parameters. Service is 46. Types of network services or protocols used within network traffic. Flag is 5. Flags indicating various packet attributes or states in network communication. SRC bytes is 0. Number of bytes sent by the source host in a network transaction. DST bytes is 0. Number of bytes sent to the destination host in a network transaction. Count is 123. Number of connections to the same host as per the dataset record. Error rate is 1. Percentage of connections that have SYN errors over a period. Same SRV rate is 0.05. Rate of connections to the same service as per the dataset record. Different SRV rate is 0.07. Rate of connections to different services as per the dataset record. DST host SRV count is 26. Number of connections to the same service on the destination host. DST host same SRV rate is 0.1. Rate of connections to the same service on the destination host. DST host different SRV rate is 0.05. Rate of connections to different services on the destination host. DST host error rate is 1. Percentage of connections that have SYN errors to the destination host. After entering all these parameters, click on predict. Here we got the result. There is an attack detected. Attack type is DOS. So in this way, by entering the parameters, we can predict the attack type. Now we will enter another set of parameters and check the attack type. So I'm entering another set of parameters now. So here I have entered another set of parameters. After entering the parameters, click on predict. So here we can see we got the result. There is an attack detected. Attack type is U2R. Now we will enter another set of parameters and check the attack type. So I'm entering another set of parameters now. So I have entered another set of parameters. Now click on predict. So here we can see we got the result. There is an attack detected. Attack type is Pro. In this way, by entering the parameters, we can predict whether attack is detected, and if attack is detected, what type of attack is detected. Now click on sign out. The conclusion of the project is utilizes generative adversarial networks to create synthetic data mimicking Underrepresented attack patterns addressing bias in AI models used for network threat detection. By integrating synthetic data representing minor attack traffic, the system's accuracy and effectiveness in identifying less common threats are significantly improved. Conducts exhaustive assessments across diverse datasets, including real enterprise data, highlighting the system's substantial superiority over previous AI-based network intrusion detection systems. Demonstrates markedly improved accuracy in practical settings, showcasing the system's capability to detect and respond more effectively to real-world network threats. Divides the system architecture into 4 core streams: preprocessing, generative model training, autoencoder training, and predictive model training to optimize the network intrusion detection system. Each stream serves a specific purpose, from data preparation and synthesis to learning representations and training models, culminating in a more refined and efficient NIDS structure. Introduces a pioneering methodology addressing data imbalance issues within AI-based NIDS, significantly improving network threat detection. By mitigating data imbalance concerns, the methodology notably enhances the accuracy and efficacy of network threat detection, contributing to enhanced security measures.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.